exposed to gravity. Then in 1929, Hubble, by studying various galaxies, concluded that the universe is actually expanding. And so if the universe is expanding, then you don't need this cosmological constant, because the forces of the expansion are going to counteract gravity. And so Einstein at the time said, oh, the cosmological constant was my greatest error. So now the next question is, well, if this is true, well, will the universe ever contract? You know, it's expanding, but eventually perhaps it'll slow down, and then gravity will cause it to contract. You know, if we had the Big Bang 14.5 billion years ago, maybe some point in the future, everything is going to start collapsing back into the Great Crunch. Who knows? So what was needed was, let's measure the rate of deceleration as the universe expands. However, about 10 years ago, two groups, including a scientist from our lab that I work with now, discovered independently by studying a particular type of supernova that the rate of expansion of the universe is actually accelerating. So it's actually moving apart faster and faster all the time. So this was a just astounding result. Why? Why is this happening? What's going on? So at this point, this is approximately what the physicists think is going on in the universe. This is the composition of the cosmos. What they're postulating is there's this substance called dark energy. And in order to fit it into the equations that they've developed, they've concluded that dark energy takes up, it's about 2/3 of the energy budget of the universe. Wow. And this is a substance that we don't know anything about, and we never knew it was there, and yet it fills the universe. Right? So we need to discover more about it. These results this result that was made about 10 years ago was based on a study of about 80, on the order of 70 or 80 supernovae. So obviously, with a sample size that small, there's going to be some room for error. And what the physicists, ever since this was discovered, the physicists have been working to narrow the uncertainty on their equations, so they can figure out more about what's going on and what is the equation of state of the universe. So type 1a supernovae are a particular kind of stellar explosion that are very useful, because it turns out they can be used as standard candles. And what they mean by that is, if you're looking at an object very, very far away, all right, the light that's coming to us may have left that object, many billion years ago. So the universe was very different then. How do we know, for example, that the laws of the cosmos weren't different then? And that's been one of the big problems in solving this problem. So it turns out these particular type of supernovae are very consistent. So it's almost like if you were trying to measure, how far is it from here to the back of the auditorium, and I had a candle, and I could measure the light from that candle, and I knew how bright it was, then I could measure the distance, right? Because I can't actually go there, right, in this experiment I'm doing. We obviously can't go to the ends of the universe. So we need to have some way of consistently measuring it. And not all supernovae are like this, but the type 1As are. They're very, very consistent and uniform. And so by studying them, that's how we're gaining the most information about what's going on in the universe. There are other methods as well, too. Baryon acoustic oscillations, weak lensing. The physicists are coming up with new ideas, but they're all kind of confirming the story that the supernovae have been telling. The problem, of course, is that we're looking for these stellar explosions, but they're extremely rare. Type 1a supernovae happen on average only about once or twice per millennium in a typical galaxy. So you have a galaxy of 400 billion stars, and on the order, once every 1,000 years, one explodes, and it's only bright for a couple of weeks, and then it starts to fade. Right? So, how are you going to find these? It's like a needle in a haystack. The universe is very big. A galaxy is huge. How are you going to find these? Well, this is where the work that our principal investigator, Saul Perlmutter, had this idea. Well, what if you just look at enough of the sky and you subtract images that you're taking now from images that were taken in the past? Maybe you'll see bright spots there. And if you do enough of it, statistically, you can show, if you look at 1 billion galaxies a night, which we do, you know, on average, you're going to find a handful of these type 1a supernovae every night. So the idea is, let's do this, and then we're guaranteed to find a couple every night, and then we can follow them up with more detail and learn more about each of these supernovae and gain tighter bounds on this equation of state and find out what this cosmological constant really is. Because it turns out, yes, the cosmological constant does exist. We don't know exactly what its value is, but we need to find out in order to really determine the equation of state of the universe. So, I already mentioned some of this before, that the supernovae were the first direct experimental evidence that the universe is accelerating, and also they have this very uniform characteristic. And the problem is that we really need a lot of spectra, and we need to capture the spectra of these supernovae over time. So you can see what happens as it gets brighter, peaks, and then the light falls off. Because you can learn, spectroscopy is one of the best ways, is our window into the heavens. Right? We can, by looking at what frequencies of light a particular stellar object emits, you can learn so much about what's going on in that explosion at this time. So we need to just collect as much data as we can, and this is the goal of the Nearby Supernova Factory. We're the highest data volume supernova search currently in operation, and our goal is just to collect the largest homogeneous sample of type 1a supernovae, and then to study that and, you know, draw conclusions from this data. And the data is coming out right now. It should say energy over there. This is the problem. Whenever I move my slides onto another computer, there's always things that are a little bit different. But essentially, that's the goal, is to just capture this very large data set and get science out of it. And this is what's happening right now. So this is an international collaboration. I put this slide up just to show that there's a very large number of astrophysicists and computer scientists in the U.S. and in France working on this problem. So it's a large experiment, and it needs a complex set of software tools in order to be successful. So the image data starts at Mount Palomar. There's an asteroid search there where they take wide field CCD images of the sky every night, and they generate about 30,000 images every night. Those images are sent to the National Energy Research Supercomputing Center, which is co-located with Berkeley Lab. And on those supercomputers, our software runs and processes this data. It's 50 to 80 gigabytes of data every night. So this is a lot of data. We need a supercomputer to process it. It's not the sort of thing that you can do on your PC at home. We cover 500 square degrees of the sky each night, and then we scan all this data and look for potential bright spots. I'll explain more about the subtraction process in a future slide. And then once we've targeted that particular object might be a supernova, then we have some time on the University of Hawaii 2.2 meter telescope on the summit of Mauna Kea, and we have a dedicated instrument, a supernova integral field spectrograph, that we point at each one of those targets, potential supernovae, and we collect the spectral data, which then goes into our database. So this is the essential idea behind how to do it. So you have the reference image up there in the upper left-hand corner, and you see a piece of a galaxy there. That's a galaxy in the corner, and then the green plus there is, you can't really see it in this slide, but it's a brighter spot. It's a brighter spot within the galaxy, which is a supernova in this particular case. And I'm sorry. You see it in the new image. You know, you can't tell the difference between the reference image, which has no supernova, and the new image, which has it. But when you subtract the two, you get something that looks like this. You get a bright spot in the middle of a dark area. And And the characteristics of this bright spot, we calculate about 20 different features from that bright spot, and then we use those features to determine, is this bright spot actually a supernova? So we get about 500,000 of these objects every night, and they need to be processed. And we have machine learning software which runs through this and selects about 100 potential candidates, which are then scanned by humans. And I'm going to describe more about the process in a later slide. Computationally, this is a very challenging problem. I've shown you a lot of images from the Hubble Space Telescope, and they're all very beautiful and very high resolution. However, these are our typical CCD images. They're filled with defects. There's atmospheric problems. There's bad weather. We have dead pixels. Airplanes and cosmic rays come through. There's this fringing, which is a characteristic CCD error. So you have an image like this, and you need to subtract these two images from very noisy data. So how do you do it? It's a real challenge, and it requires pretty sophisticated image processing software to do this. And remember, you have to do it fast too. You can't crunch on this thing for a couple days. Since you're doing 500,000 objects a night, you need to farm them all out to a supercomputer, and all of your algorithms have to be very efficient. So when I was brought in, okay, so let me step back a little bit. So the project this is going to be a success story of an interdisciplinary collaboration. So about 3 years ago, the project was being done just by astrophysicists. They were all very smart, but astronomers have, in the past, almost, because they had a very small number of supernovae, where you might just have one supernova, and then you'd spend months analyzing it. So they were very used to an interactive way of, dealing with their data. They weren't used to this, scaling up. All right, they didn't have the experience in building software that would do that, and so they thought, well, we'll just hire one grad student. They'll write a program and it'll be done. All right. Well, as computer scientists and software engineers, we know that just doesn't work. Right. But even though they were very smart people, they hadn't yet made that scaling transition, which is hard sometimes to understand. So I was brought in because the project was not successful. All their software was failing, and they had this very expensive telescope time which was going unused because the data wasn't going through their pipeline, which had been written by a couple of grad students who then left. No documentation. The code was just left on its own. All right? So what do you expect? So when I came in, they had the supernova search code, which had a lot of very sophisticated algorithms, which worked very well on individual images. All right, they just weren't scaling up to this, let's run 30,000 images a night, 500,000 objects each night. And then they also had a lot of very crude interfaces. This is another, since I'm a visualization specialist, I work in human-computer interaction, one of the things I see is that a lot of scientists are still doing things kind of the old way, where you get data, you email it to somebody else, they cut and paste files into another computer. Well, that works okay if you just have a small amount of data. But what happens when you have terabytes of data, which is what we're going to get with the new physics experiments, the new telescopes which are coming up? We're going to have huge amounts of data. How are we going to process it? Well, we have to be ready. We have to be able to build systems like this, and that's really going to take these large interdisciplinary collaborations. And this is really kind of a prototype, I think, of how the future is going to be in large-scale science. So anyway, so then the scanning was where the humans looked at these images. They visually looked at these subtraction data, and they said, oh, this looks like a supernova to me, or this looks like junk to me. This is an error. And they had about, they spent a lot of, it was a large collaboration. They spent every day, about 6 or 7 of the scientists spent, 3 or 4 hours looking at all this data, scanning it, and deciding whether it should go to the next phase. So essentially, and then they had to look at other websites to say, well, this thing looks like a supernova. Maybe it's an asteroid. Let's check this other database. And they had to go to this other database manually. Is there an asteroid at this particular location? So essentially, the point I'm trying to make with all of this is there was a lot of human invention, a lot of wasted time when the scientists were really doing grunt jobs. They weren't doing science. Right? So the problem that that when I was brought in to evaluate the problem, it was not just that I needed to develop better software and better algorithms. Also, there was a need to develop better interfaces between the scientists and the data. All right, so this just repeats what I said before. There was a lot of repetitive work, and morale was low because science wasn't getting done. You know, if you're a physicist, you want to do physics. You don't want to be moving data around and scanning images all day. So it was a challenge. So in the past, the way these problems were dealt with is they said, let's bring in a computer scientist, we'll have one meeting, then the computer scientist will go off, they'll write some code, and then they'll throw it over the fence back to the science collaboration, who'll then use it. Well, you know, this just wasn't going to work in this case. And this, I want to credit, you know, Greg Aldering, who's the leader of the Supernova Factory, for really recognizing that this wasn't going to work. The leaders of the Supernova Factory, including Saul Perlmutter, realized that, you know, what we need is something different. We need an interdisciplinary collaboration. We need to bring computer scientists in to work on this problem, and they need to be co-located with us so that we can see them every day and so that we can all work together. So we were actually embedded in the physics group. What that meant is, you know, we all moved up to the physics floor. We had offices there. I hired a team of people to work on the project. And I was tasked to come up with architecture for the system and to, you know, bring in to get all the people to work together on this piece of software. So these are the contributors to Sunfall, the Sunfall framework. And I bring this slide up just to say that it was the work of a lot of people and people from, and this was our team. It's unusual to see a team like this. That's, you know, a large portion computer scientists and engineers and a large portion physicists. But it was very successful. So if any of you have the opportunity to encourage, you know, funding in interdisciplinary projects, I want to say go for it. It's very successful. If you have a chance, if you're either a scientist or going to be a computer scientist, interdisciplinary collaborations are really the way to go. For the computer scientists, you get to work on real problems. You get to do your research and know that you're making a difference. And it really focuses your research and makes it more tangible. For the scientists, you get to get the latest techniques from computer science brought into your field, and it really gets to solve some of these very intractable problems. So the tool that we eventually designed, the software framework, was called Sunfall for the Supernova Factory assembly line. We used, you know, this motif of the factory sort of came up, it was partly a joke, but the idea was, you know, we worked 24/7 on you know, there were shifts, right, because we were getting in the data all the time. Every day you get more data, so you really have to work on it. You work weekends, you work nights, and you take turns doing it. And so we wanted to create this assembly line which would reduce the need for human intervention and put more of the load onto the computers. And as a result, we ended up creating this very interesting visual analytics framework. It's actually the first visual analytics system in applied to astrophysics at all. And we discovered there were interesting computer science problems all throughout the software process. So we did workflow management, which is a new and active area of research in computer science. Scientific data management, this is a big and important research problem. As data just gets bigger and bigger. How do you handle a terabyte of data? How do you make sense of a terabyte of data? You know, you can't look at all the numbers, and you can't put it all up on a screen and visualize it because you don't have that much room. You know, you've got on the order of a megapixel of data on your computer screen. So how do you do it? Visualization is very important. Data analysis is very important. You want to combine all these two together, and it must be interactive. The computer can't do everything on its own. You have to have the humans being in the loop, but you have to make it very efficient so they're not wasting their time. You want to save the time. The scientist's time, the user's time is very valuable, and you want to focus on the things that humans do well and computers do badly, and let the computers do everything else. And of course, we had 150,000 lines of legacy code, and we had to use that. That wasn't actually our choice. We would have loved to rewrite it all, but that was a mandate as part of the project. So we had to build our system to incorporate the legacy components, which is actually pretty typical in software engineering today. So the point of this slide that I want to make, first of all, is I talked about the 4 components of Sunfall, but I want to also say that even though this is applied research, that, which sometimes people in any field will look down on interdisciplinary collaborations because, well, it's applied, it's not pure, it's not as important. But I want to say that we've gotten a lot of publications out of this work, both in astrophysics and in computer science in many different areas, and we're still writing. I just submitted a paper last Friday, actually, to a conference on computer-supported cooperative work. And so the point I want to make is, if you're choosing to go into applied or pure research, applied research you can have a good publication record in this area as well. So this is the architecture, a very high-level architecture diagram of the supernova framework today. Notice the difference before. We've reduced human involvement. In some areas, we actually have up to 90% labor savings. As a matter of fact, when we had this, I'll have a slide later on that shows this in more detail. But the scientists estimated that we went from about 6 full-time scientists working on this project to 3/4 of a scientist. And what that means is all those other 5 scientists are now doing science. They're working on the stuff that's going to win them the Nobel Prize. So all the blue areas are the legacy code that we wrapped in this framework. We had existing databases, and we also built our own set of databases. We set up a new mechanism called the data forklift for transferring data from one computer to another. Remember, this is an international collaboration, right? So we get data from San Diego, it comes up to Berkeley, then it goes out to Yale, it goes to France, it goes to Hawaii, it goes back to France, and then it comes back to Berkeley. All right, so we're doing a lot of data transferring. We want that to be as efficient as possible. So we had a special mechanism that was designed to do this, and this works, again, 24/7. So the scientists aren't the ones who have to cut and paste, and move files using, secure FTP. That all happens automatically. That's what the computers do well, and we let them do it. Finally, we developed a completely new system called the Supernova Warehouse, which is a visualization and data management system which greatly increased the efficiency of the scientists in dealing with their data. And it's still in use today. This is another thing that you'll find oftentimes when you talk to computer science researchers. They'll say, oh yeah, I built this really beautiful software. It's very innovative. It's very different. You say, well, who's using it? Well, it was just a prototype system. We don't have funding for it anymore, so we're working on the next thing. Well, you know what? The scientists are still using our tool, and they still want it. All right, and we're not developing it actively, but they have an engineer now who's maintaining it, and it's an integral part of their of science discovery for them. So now I'm going to talk in more detail about the 4 components of Sunfall. So first of all, the search. So I mentioned before the problem with discovering a supernova, dealing with this very large set of data, subtracting the images, and coming up with something which might be a supernova. This is where we had a very great increase in human efficiency because we were able to both improve image processing algorithms. We came up with a novel Fourier contour analysis algorithm that detected whether those targets were round. Okay, believe it or not, this is something that the original software didn't do. Sometimes they would get these sort of C-shaped things, and these were still being presented to a human who, of course, could instantly see that it wasn't a supernova. But I said, well, I said, I know about Fourier analysis. I think you can do shape detection with this. This is from my background as an image processing person. And they said, oh, Fourier analysis, that's much too complicated. And remember, everything has to be done in 10 minutes per image. We don't have the time for it. So I and another person worked on this, and we came up with a linear time algorithm that actually walks the contour and detects this in linear time, and it's linear in and the number of pixels in the contour, which is very small. Actually, it's on average, it's on the order of 15 or 20. So it's an amazingly fast algorithm. Didn't add anything at all. It was negligible, the amount of time it added to the system. So that was a big success. Then we also, when we first came in, they weren't using machine learning to, believe it or not. I mean, it seems like an obvious thing, but the program was written by a grad student who was in physics, who was unaware of machine learning techniques. And so they just basically said, well, we have these 20 features. We're going to have a minimum and a maximum for each of them. And that's going to give us this, this rectilinear cube in 20-dimensional space. And we're going to adjust the size of this based on, whether we're getting enough supernovae or there's too many bad candidates coming in. So we brought in first support vector machines, and that had a dramatic impact on the number of candidates that were sent to humans. That really cut down the amount of time they were spending scanning. And then we actually refined it some more by applying boosted decision trees and got a further improvement. Then we also had just improved control interfaces for the scanning process. This is very simple, but we just, we did kind of like an efficiency analysis. I'll talk a little bit more about that in the next slide. So essentially, I already mentioned this. We got about 90% labor savings from this alone. So this is a description of the improved control interface. When I came on board, they were looking at each of these images individually by sending out an email and then cutting and pasting this image and looking at it one at a time. So it took about 2 minutes to look at each image and decide whether or not it was a potential supernova. So we built a little tool which it layers over their existing code so they don't have to change anything, and it's just a faster interface. Now they can click through each one, and it turned out this saved them about 30 seconds. It got them down to about 30 seconds per object. So it's very simple, but it turned out very effective. Right. Okay, so the next piece of Sunfall was what we call the Sunfall Workflow Management Status Monitor. And this is essentially just a dashboard. Again, this is something that's very common in web-based applications today. It's a way of centralizing all the data, all the status about the workflow in one place. The way it was before is, we had this large and complex pipeline running through the supercomputer, and it turned out that there would be errors, and the code was buggy, and so it would crash, and somebody would need to patch it up. And sometimes people wouldn't notice it because you didn't have all the information at once. So we gave them a visual tool that each of these graphs are gathered, were taken from the supercomputer, and instead of the individual having to keep logging in and checking 5 or 6 different places, they could just keep this dashboard running on their workstation. Now, home, it's remote, so if they're monitoring the system late at night from their home, they could just check on this and they could instantly see whether there was a problem. So again, this is, very simple technology, but it was very effective. So you can see kind of the tone of what I'm taking here. By bringing in the computer scientists, we were able to produce both novel algorithms and also just apply some simple techniques which greatly improved the problem. And what I want to say, too, is that I don't want to say that it's just that the computer scientists did this work. We worked together with the physicists, and they did a lot of the implementation. Right? So it was a group effort. All right, so here's the third component of Sunfall, the Sunfall data forklift. So we have this heterogeneous distributed data all over the world on all these it's in different databases on different classes of machines, and it needs to be processed, managed, and displayed. All right, how do we do all that? The data forklift is essentially just a suite of services that provides secure and automated data storage, retrieval, movement, querying, and staging for display. So what was important about the data forklift is it's secure, it was authenticated, so we provided all that, and we provided all that data seamlessly. All right, so again, this was a pretty complex system, but none of the techniques that we used in and of itself was extremely novel, but the combination was very novel and was very effective. Just to step back a little bit, so I actually think the data forklift, the tools here, this is a problem that I think many science I think basically any scientist will tell you they have today is the data is heterogeneous. It's scattered, it's distributed all over the place. Everybody has a different format, and because of it, you're not getting as much science discovery because you can't see all of the data. So I personally believe that this type of tool is going to become more and more important in the future. As you know, you're not going to be able to move all the data and centralize it into one location. It has to stay where it is. And what you're going to need is tools to manage that distributed data flow, that heterogeneous distributed data. And it's a very interesting problem, and there's a lot more work to be done in this area.
So are scientists coming up with their customized ways to put it together, or are there standard things that you do and that gets run by a script?
Yes and yes. I mean, it varies, of course. You know, there are some scientists that say this is our data format. We're not going to change it. This is, you know, we have this code written in Fortran that we rely on. We don't have the budget to change it. It's going to come out in this data format. So, you know, and that for those particular scientists, we might write a conversion tool, for example. All right. And the other thing we're trying to do at the lab and at NERSC in general is we're trying to encourage standardization on different data formats. And so, you know, one of the things you do is you hope that there's eventually going to be a standardized data format that's generally recognized, and that will sort of like the HTML of science, right? And this is happening in more fields now because scientists are recognizing this problem, all right? But part of what we do at the lab and in our group is, you know, we work around that. For people who are willing to convert and work in a standard tool, we offer tools that help that, and that makes it easier. And for people that aren't, we write the conversion tools. You know, it's an ongoing process. And then you bring it all together. All right, so these were just the requirements for the data forklift, and I think I mentioned some of them before. The service is actually run at a central location on our server. But another key is that it's reliable and self-restarting, and it's fault-tolerant. There's a lot of unreliable connections. As anybody who's dealt with the internet knows, connections go down, machines go down. You need to be able to recover from errors. That's critical. That was a very big problem with our collaboration, and when I've worked with other scientific collaborations as well, they have the same problem. You know, how do you recover from errors? It's not easy, and you need to be able to do it cleanly. We built the forklift so that it's extensible, so that if a new type of data becomes available, we can add in a service that processes that very easily. It can read, you know, if necessary, it can read external websites. It parses the data and brings it into our system. And user actions can trigger forklift requests. So if a user says, you know, there's 5 gigabytes of image data from this day and in this particular piece of the sky, I want it now, they can request the forklift to get it, and then it'll be there for them. Finally, the fourth and most visible piece of Sunfall is the Supernova Warehouse. This is a tool we built it in Java. It runs in a web browser. So this is convenient because our scientists might be using Unix or Macs or PCs. They're going to be they might be located in their homes. They might be in France. They might be at a conference. They need to be able to check on the data anywhere in the world at any time. They might be up at the summit of the telescope, right? So essentially, we built a couple of custom visualizations that made it easy for the scientists to understand what's going on in the night sky at any particular time. And we also centralized all the data, all the supernova data in one spot. This has the advantage, for example, I went to all their weekly meetings, so I got to sit in and see some of the benefits of the tool. For example, when I first started, you would go to a meeting and a scientist would say, "Oh, didn't we observe a supernova back in May that was like this one that somebody just wrote a paper on and we're all very excited about?" And then in the past, they would have had to send a graduate student out to look through the old data, bring it in, and report back on it the next week. As it was, somebody just flipped open their laptop, brought up Warehouse, and within 5 minutes they said, "Yes, we observed supernova 2007 SJ in May, and we have 12 spectra of it, and here they are. And we can all look at them and compare them with the spectra in this published paper. So you could see that, that really, this is what science discovery is about. When you get an idea, when new information comes in, you need to compare it with existing data so that you can think about it, right? Waiting a week isn't going to work. So these are just further images from the tool. It analyzes it brings together not only the visual data, the image data, but also the spectral data. So for each supernova, they have a little thumbnail of what the spectrum looks like, and then they can drill down into a graph of it or even the raw data itself. They also have all the associated metadata, so they know its provenance. They know what the weather conditions were like when this particular spectrum was taken. They know what scientists classified it as a type 1A or a different type. Data provenance is really important to the scientists because they trust some scientists more than others in terms of classification of the data. And those two little visualizations, the purple and green there, also help them determine whether the spectrograph was actually centered on the target or not. So it actually it's a visual indicator of the quality of the spectrum, which they can use as well to make their determinations. So essentially, we're bringing in this large amount of data, we're presenting it to the scientists in a way that's very fast. This is the human visual channel is the highest bandwidth sensory channel that we have. And as we move into large data scientific problems, we're going to need to really maximize the efficiency of the interface between the data and the humans. So this is just a slide that I made because I was really proud of the work that we did to save the scientists time. So we actually analyzed how much time each of these tasks took before Sunfall was implemented and after. And if you're looking, for example, a physicist might say, well, why do we want to spend money on expensive computer scientists to work on this system? Well, the answer is here. It saves time. It saves staff time. And the important thing, too, is that it's not like these staff were let go. They were now working on solving the important scientific problems. Since I've worked in industry, I have some background from that. I'm not just from academia. So I talk in terms of return on investment, which is of value in academia as well because, we all need to, we survive on grants and we need to prove that we're delivering value for our grants. This tool took about 1.5 years to deploy, and it was about 5 person years. A lot of the people involved were also working on other things as well. But it paid for itself in operational costs alone within 1 year. And also it enabled new science discovery, as evidenced by the number of publications that we had after the tool was developed. And it reduced significantly the number of data-taking errors and enabled more science data to be collected. So essentially, this is the slide that I use when I talk about the benefits of collaborative projects and interdisciplinary projects to management in both physics and computer science. We were able to show a significant, a measurable effect on a major science project. And this, as I said, dark energy is one of the key, it's a grand challenge in physics today. This is where the physicists are putting a large amount of effort into solving this problem. I already described the numbers to show the benefits that we produced. We also demonstrated this new capability. We deployed a production analytics workflow. It was the first one that was deployed on NERSC supercomputers. And this was really the proof of concept that this type of collaborative relationship can have a profound impact on data-intensive science. And we always look at publications in the end. Have publications resulted from this work? And the answer is yes. If you just look at the computer scientists working on this project, in 1 year we had 4 computer science publications, 4 refereed computer science publications, 2 refereed physics publications in the top journals, and 35 non-refereed publications such as posters and astronomical telegrams. And we're still producing more work. So there's more work, more good publication is yet to come. So that's That's all I have now. I'd like to open it up for questions. Yes.
So
Oh,
we're
sorry.
actually televising this to some of the CASI institutions around the country. So I'm going to turn on the phone to see if there's any questions coming from across the other institutions. But go ahead and ask questions here.
It does. Yeah, it actually does more information, heterogeneous information transfer. It does some. It's more information collection. I think there's only one particular case where we transfer data from one format to another specifically. What it essentially does is it runs and collects different types of data and centralizes it all in one place so that we can then process it and, you know, we can all process it all at once. So it's useful in terms of temporal collaboration as well as we do synchronous collaboration with a bunch of people working together where we use the data forklift to transfer data back and forth, and also asynchronous collaboration where data might be generated by one group overnight, like in France while we're sleeping here, and the data gets transferred over by the forklift, and so it's waiting for the scientists at Berkeley lab in the morning.
Okay, so basically my question is, suppose that we open this architecture to other groups to join in.
Yes.
What would be the semantic issues about data from other sources?
Well, okay, it could, yes. This particular set of services was designed to be extensible. So if somebody else was interested in, you know, if somebody else had data that this particular collaboration could use, yes, a forklift service could be written fairly easily and integrated in with the existing tool. So it was designed it was designed to be extensible. So that could be done. Now, if you're saying, what if somebody else wants access to the collaboration data? That's a separate issue, and that's something that's going to be worked on in the future. I mean, as a matter of fact, I'm working on another project where we're talking about how do we gather all the data that's been collected here and make it available to the public in general. Was that your question, or?
The question was basically if some new group come in and they have different meanings for the terms.
Different meanings for what terms?
So gravity, they measure in a different form, in a different way, and then you need to use that gravity, but it's not just a single translation, you need to do further processing. So you have different semantics for what they mean.
Oh, different semantics for, yeah, that we can handle. I mean, that, we've had to do that anyway right now. Each service, you know, will deal with, you know, for example, asteroid data might be called transient data in by one particular group, and another one might call it an asteroid. It's all part of the metadata tags. We store all the provenance. So part of what we would do is we would store the metadata associated with both names so that we have a method of translating from one to the other. And so both groups could access the data using whatever name they preferred to access it by. I hope that answered your question. Yeah.
I just have a final one. If they use the same term for different things.
If they use the same term for different things. The way we would handle that is we would tag it. So there, you know, for example, let's suppose the group from Yale called it I'm just making this up, called it A, and the group from Caltech called it B, or called it A as well, but it was two separate things. We would have Yale A and Caltech A, because we gather all the metadata. Since we store all the provenance of the data, you know, calling different things the same name isn't really a problem because we have all that other, you know, all the other data provenance as well. Okay, thanks. Any other? Yes? I can't hear you. Can I explain a little bit more about the fault tolerance mechanisms? It's a general framework. The way it works is it's different in every case. I mean, fault tolerance is a very difficult problem. And the one example, okay, so on the supercomputers, one of the typical problems we had is that an image was being processed on one node, and then the node would go down. You know, we have a 200 or 400 node computer, you know, or we were using IDL and there weren't enough. It's a proprietary software. Don't use proprietary software. You know, you run into license issues, especially when your budget gets cut. But anyway, so we wouldn't have enough licenses, and so some of the data wasn't being processed. And what would happen in the past is there was no reporting mechanism. So the data would just disappear. There was no error message sent back. It would just go quiet. So one of the fault tolerance mechanisms we implemented was after a certain amount of time, you know, we take that, if we don't hear from a particular node, we'll take that job and we'll move it to another node. All right? And then we'll make sure that the database, if it's been partially updated, we actually roll back some of the partial results associated with that job. And then we continue on, and so we send it off to a new node, and we flag that existing node as potentially bad, so we try not to send new jobs to that one as well. All right, so, but then we manage the whole system. What you'll sometimes see is that a number of the nodes have gone bad, and so you're rerouting, you need to reroute the jobs to other nodes, and some we were able to catch most of the errors with the software framework, but not all of them. So the other tool we had was the dashboard, the workflow status monitor, and that enabled a person to look at it and say, oh, I detect an error right here. And they were able to reroute it manually. So we didn't catch everything, but what we did catch, but what we didn't catch, the scientists were able to detect rapidly and route around. So as a result, when we started the project, there was something like 3% efficiency getting all the data through the pipeline when we started. And at the end, it's pretty close to 99% efficiency. Yes?
One of your slides, you mentioned that you compare, let's say, a model with something that you're reading, and it said that you manually specify the threshold.
Okay, yeah, in the subtraction pipeline. Yes, that was the old method, yes.
So I was wondering, how are they specified now? Are those specified with some sort of language? Are they... The old way was they had about 20 features for each sub-image, and they were just numbers. Okay, so they had a minimum and a maximum. This is a piece of IDL code, which I edited, so I know it very well. There was a minimum value of feature 1, maximum value of feature 1. You get the value for this image, and you compare it. Is it within this range? And that's how they did it for each of them. And that's what we modified to apply the machine learning techniques and made it actually a lot more efficient, because if you think about it, having those thresholds, you actually have if you imagine a bunch of samples in n-dimensional space, and then if you create this basically a rectangular prism in that space, you may not be separating your good data points from your bad data points. So you actually want to have some sort of multidimensional surface which separates the good supernovae from the junk images. And that's where the machine learning algorithms were so useful. Any other questions? Yes?
So you said that scientists may not trust each other equally. And the question I have basically is, do you have somewhere in the system saying scientist A does not trust scientist B?
Of course not.
Okay.
Of course not. But you know what I mean. I mean, when I say they don't trust each other, it's like let's say you're a Nobel Prize winning physicist, and you see that a grad student that you've never heard of has classified this supernova as a type 1a. It's not that you necessarily don't trust them. You might say, oh, well, I want to look at the data, and I see that it was classified by this grad student at this point. And you say, well, I disagree. All right, and so you can then reclassify it, but the provenance still stays in there so that you can see it. So later on, if it turns out the Nobel Prize winning physicist was wrong, the grad student gets credit for originally discovering it. We don't delete anything. We save all the data provenance, and that's what the scientists like, because this is part of science discovery, right? You learn from each other's mistakes, and certainly you would never say that somebody's not trustworthy, right? Everybody is, these are all really smart people, okay? But nobody is 100% perfect. Any other questions?
So let's thank our speaker, and
Thank you very much.
We weren't able to get the questions from the other institutions, so I apologize if we didn't get your question. But thank you very much, and thanks everyone for attending.
And thank you for having me. Yes.
What image processing you do in this data besides like the contour that you showed? What more you have?
Which
Do
more?
Yeah, and I was surprised like you used Fourier. I was expecting wavelets. Yeah.
Yes, that's
Something
right.
like-
Well, we consider all this. We have papers on this. You know, oops, I better take this off. Yeah.